Welcome back. In this lesson, we're going to be looking at the addition of two positive 8-bit binary integers, and we're going to understand the concept of overflow and why it occurs in binary addition. We're also going to be looking at logical binary shifts on positive 8-bit binary integers and understand the effect this has on the integer itself. So how do we do multiplication and division? Logical binary shifts play a huge part. And finally, we're going to be looking at how we represent negative 8-bit binary integers using 2's complement. And we're also going to look at how we can use the same system to represent positive binary integers and perhaps work on a calculation which will involve both positive and negative binary numbers. This is going to be a bit longer than the normal lessons because there's a bit of maths involved, but it's pretty simple maths and it won't take you that long to understand it. Okay, let's begin. Now, at this point, I am assuming that you know how to convert binary to binary and hexadecimal and vice versa. If not, then please go to the previous lessons so you have a good grasp of how those conversions work. Now, computers can do calculations really quickly. The word compute basically means to calculate. And this is the primary purpose of a computer. And that basically means maths, addition. Computers are very good at doing calculations, billions of calculations per second. The addition is just like our normal addition, where we add two numbers together and it gives us an outcome. And there are a few rules. For example, if you add two zeros, it gives you a zero. If you add a one and a zero, that gives you a one. That's pretty straightforward. Now, if you add two ones together, in our denary maths, we normally get two. But in binary, we get a zero with a carry of one. Because if you think about the binary two, that's 1, 0. So that's what you basically get, a zero and a one carried over to the next column. And if you add three ones together, you now get three, which in binary is a one and a one. So you have one and another one carried to the next column. And these are just the basic rules. There's nothing else you need to know about binary addition. So as long as you can memorize these rules, the addition works pretty straightforward. Now on screen, there are two examples. In the first one, I'm just adding a single bit to a binary number. So 1101, 0010 at the top, and I'm adding a single bit to it. So what happens is that the last column, the rightmost column, the 0 and 1 changes to a 1. Everything else stays the same. So the answer is 1101, 0011. In the second example, though, I'm now adding an 8-bit number to another 8-bit number. So 1101, 0010, I'm adding 0010, 1010 to it. Now the rightmost column, 00, that gives me a 0. The next column, however, has two ones. So according to the rule, that gives me a 0, and the 1 gets carried over to the next column. In the next column, now I have two zeros plus a 1, which means that I get 1. Two zeros are a 0, and the 0 plus a 1 gives me a 1. And I keep doing this for the rest of the columns, and in the end, I get 1, 1, 1, 1. 1100 as my answer. And that's all there is to binary addition. It is pretty straightforward. But what happens sometimes as a result of this addition is that if you've got two 8-bit numbers and you basically have two ones in the leftmost bit, that will give you a 1 with a 1 carry, and that 1 flows over to the ninth bit. But since we're using 8-bit, this extra bit falls off because we can't fit that in to the existing 8 bits. This is called overflow. So an overflow error normally occurs if the value that you've just added is greater than 255 in an 8-bit register, or it can't fit in those 8 bits. All computers have a predefined limit that it can store. So that's why we get like 16-bit computers, 32-bit computers, 64-bit computers, and so on. So an overflow error occurs when a value outside this limit, which is a fixed limit, is returned and it can't fit into the allocated bits, because in the end, computers have physical parts and you can't magically create a physical part if you need it. So the concept of overflow is really important. It can lead to errors, but it can also be very useful when we're doing subtraction, as we'll see later on. Okay, before we move on to subtraction, I'm just going to talk a bit about logical shifts, which is basically multiplication and division, if you wanted to equate that to a mathematical operation. Logical shifts use something called shift registers. And shift registers are just temporary storage areas, which would be 8-bit, 16-bit, and so on, where you can store numbers or bits in. A left binary shift or a 1-bit left binary shift is the equivalent of multiplying by 2. So if I move a bit to the left of it, That means I'm multiplying the original number by 2. So if you think about it, if I have 0, 0, 0, 1, and I shift that 1 place to the left, I now get 0, 0, 1, 0. So the original number was 1, the new number is 2. Now if I shift it once again, 0, 0, 1, 0 becomes 0, 1, 0, 0. So the initial number was 2, and then the new number is 4. So shifting one bit to the left is simply multiplying by 2. Shifting one bit to the right is the equivalent of dividing by 2. This makes multiplication and division very quick for a computer to do. They don't just have to work anything out. So if you want to multiply something by 8, you just shift the bits 3 places to the left. Now do pause the video and have a look at the example on screen. The only bit that I want to highlight here is that if you're shifting bits, eventually the most significant bit, the bit that's on the left hand side, will lead to an overflow because it might drop off, and that means you lose some accuracy or some value. And the same rule applies when you're using right binary shift, which is the equivalent of dividing. In this particular case, the least significant bit, the one on the right hand side, is lost, because if you're shifting everything to the right, eventually if you add a 1 to the right, it'll just drop off. Again, pause the video and make sure you go through the example of the right binary shift. If we shift by 1 to the left or right, that's the equivalent of multiplying or dividing by 2. If we shift 2 bits to the left or 2 bits to the right, that's the equivalent of multiplying or dividing by 4, and so on. So each shift is times 2. We can shift multiple bits, and each bit shift increases the multiplication or division factor by 2. So if you've got 0, 0, 0, 0, 0, 0, 1, 0 shifted 4 to the left, it becomes 0, 0, 1, 0, 0, 0, 0. So the 1 is shifted 4 places to the left. And that's the same as multiplication by 2 times 2 times 2 times 2, which is 16. So if the original number was 2, the new number is 2 times 16, which is 32. And similarly, we can do that division. So in this case, we've got 128 shifted 4 places to the right, which becomes 0, 0, 0, 0, 1, 0, 0, 0, which is the same as division by 16. So 128 divided by 16 is 8, which is what the binary gives us. So pretty straightforward. Do pause and do check the maths yourself if you're not sure. Of course, you can play around with multiple shifts here as well. A shift register contains the following value: 0010, 1100. A number of shifts are performed on it. So it's shifted 2 to the left, then 3 to the right, and then 2 to the left. What are the contents of the shift register after these operations are complete? Now, in order to do that, you can do it individually, or you can just work out the collective difference. So 2 to the left, 3 to the right, 2 to the left. So there's 4 to the left and 3 to the right. That means 4 minus 3, that means 1 to the left. So that means this one will be multiplied by 2. So we just shift everything 1 bit to the left. So in this case, the answer will be 0101 1000. You can also do that in another way. Here, a shift register contains the following value: 0000, 1010. The contents are multiplied by 8, then divided by 4, and then multiplied by 2. What are the new contents of the shift registers in both denary and binary? So here, you will need to work out the shifts. So 8 is shifting it 3 to the left, dividing by 4 is shifting 2 to the right, and multiplying by 2 is shifting 1 to the left again. So technically you've got 4 to the left now and 2 to the right. So that means 2 to the left. You shift everything in binary and then you work out the value in denary. Try to see if you can work this out yourself, or get back to me if you have any problems. Hopefully that was okay for you. Let's look at representing negative numbers now. Now, negative numbers are important in the real world because we need to represent deficits or things that are taken away from us rather than things that we accumulate or increment. So in our denary maths, it's pretty straightforward. We take a symbol, which is the minus symbol, and we use that to represent a negative number. Now that's quite tricky in binary, where you only have 2 digits available, 0 and 1. There is no space for minus signs and plus signs and all of those kind of things. So we've got to work out a mechanism of representing negative numbers using 0 and 1 and the amount of bits that we have. And there are a couple of methods which are quite common. The first one is 1's complement. In this case, we just invert the binary number for the negative version. So if you have denary 90, which is 0101, 1010, we invert all the bits. So that means we flip the bits. So 1 becomes 0 and 0 becomes 1. So in this case, 0101, 1010 becomes 1010, 0101, and that's denary negative 90. Now the problem with this particular method is that it can lead us to a negative 0, because imagine you have all zeros: 0000, 0000, flip the bits, and that becomes 1, 1, 1, 1, 1, 1, 1, 1, and that's negative 0. So 1's complement has a bit of a problem. Therefore, we then use 2's complement, which is the most common way of representing negative numbers because it avoids that negative 0 and it makes addition and subtractions of binary numbers just like denary. So how does it work? Well, we do exactly the same thing. We take the original number, which is denary 90, 0, 1, 0, 1, 1, 0, 1, 0. We flip the bits. So it becomes 1, 0, 1, 0, 0, 1, 0, 1. And then we just add 1 to it. So therefore, the new number becomes 1, 0, 1, 0, 0, 1, 1, 0. So the 1 and 1 gives you a 0 and 1 carries to the next column. And you can check this because in 2's complement, the place values are minus 128 and then positive 64, 32, 16, 8, 4, 2, 1. So the leftmost significant bit becomes a negative number. Now, another issue with using these mechanisms to represent negative numbers is it reduces the range of numbers we can keep in whatever allocated bits we have. So in normal 8-bit binary, we can store all the numbers between 0 and 255. But by using this representation mechanism, the range is cut in half. So the numbers now range between positive 127 to negative 128, which means that I can't represent numbers bigger than plus 127 using 2's complement or 1's complement. And that can be a problem in some cases because I now need more bits to represent bigger numbers. So let's test this out. Let's convert 117 to negative 117 using 2's complement using 8-bit binary. The first step is to convert 1117 to binary, and we've got that on screen, 0, 111, 0, 1, 0, 1. We flip the bits, which then becomes 1, 000, 1, 0, 1, 0, and then we add 1 to the rightmost bit, so that becomes 1, 0, 0, 0, 1, 0, 1, 1. This is the 2's complement version of minus 117. So let's check that out. Put the place headings and put this binary number in there. So the first one is minus 128. Then we got 3 zeros. Then we got 8. Then we got 0. Then we got 2 and 1. Now minus 128 plus 8 gives you minus 120. Plus 2 gives you minus 118. Plus 1 gives you minus 117. So the maths works out. Do pause the video and go through it to see if you understand the process and how we can check if the maths is correct. Try to work out the following. What's minus 114 using 2's complement in 8-bit binary? What's minus 225 using 2's complement in 8-bit binary? And then try to work out the calculation 24 minus 12 in binary. Pause the video and try to work all of these out, and when you're ready, continue. Hopefully you got something like this. And for minus 225, you should have realized that you can't fit that in the range because in 8 bits, we can only go between minus 128 and positive 127. You would need more bits to store minus 225. And for that expression, 24 minus 12, you should have converted 24 to binary, which was 0001, 1000, with 16 plus 8 is 24. Then you convert 12, which is 0000, 1100, flip the bits, add 1, which then gives you minus 12, and then you just do normal addition between 24 and minus 12, which gives you that number 100001100. Since the left one overflows and it won't fit in the 8-bit binary, it can't be counted. Therefore, the number becomes 00001100. And if you look at that, that becomes 8 plus 4, which is 12. So 24 minus 12 gives us 12. And that's pretty straightforward if you think about it, and very easy for a computer to do without a human being involved. So we can automate that process, transistors and registers, and a computer can do calculations by itself without any human intervention. Okay, that's all for this particular lesson. Hopefully you can answer the following questions. What is meant by overflow? What are the 4 addition rules? Explain how logical shifts work, both left shift and right shift. You should be able to use 2's complement to convert numbers like minus 57 in 8-bit binary or perhaps larger. In the exam, you'll probably be only asked to do 8-bit binary. And you should be able to perform binary addition, which could be something like 1000, 1101 plus 0011, 0111. That's all for this particular lesson. If you do have any questions, get back to me. Otherwise, I'll see you in the next one.